In last week, we talked about the problem according to minorly weighted structure. More likely for such kind of BW instead of BMW. Okay, minorly weighted structure, it will always cause some kind of glitch. Anyway, we have some way to handle it. We call it the glitcher. Yeah, actually, it is some kind of simple and hold. However, if you operate the DAC at very high speed, sometimes you cannot make it because the period is too short for the output waveform to be stabilized or to settle down. Anyway, you will still see some instead of all of the glitches. Okay, so what we can do? Anyway, from the beginning to reduce the magnitude of the glitch. Actually, minorly weighted structure is never a good way. If you would like to pursue the best performance, you always need to come back for such kind of unit devices. So here, for the best performance, you need to focus on unit current source, just like this. Yeah, and it means for n bits, you will have totally 2 to n's power minus 1 current sources. Everybody will be the same. Everybody only carry 1 unit of current. So you can see if your digital input is 100, what does it mean? 100 of them will be turned on. The others will be off. That's it. Okay, so it means that the number of the unit currencies to be turned on is exactly the same as the input value. Okay, that is the idea for such kind of unit current source structure. In this way, we can promise you the so-called monotonicity, because never mind all those unit current sources are exactly the same or not. If you increase the input value by 1, you need to turn 1 more unit current source on, right? So totally, the output current will be increased. That's it. So you can ensure the monotonicity. That is the best way for current source structure to achieve the best performance. Yeah, and again, to get the fully differential output, we have this for V out plus, okay? And the other one for V out minus. So for each switch, the current will be turned to the right if the input is 1, or to the left if the input is 0. That's it. Okay? However, we need to meet the same problem as I mentioned it last week, I guess. Yeah. Anyway, totally, there are so many switches to be turned on or turned off. You need something called minorly to thermometer code encoder or decoder. Sorry for that. I have no idea. Yeah, because I have a very poor memory. Anyway, encoder, maybe. Okay, because for 8 bits, totally you need to have 255 output bits to control all the unit sources, right? It is a huge structure. If 1 more bit is required, then the size of such kind of minorly to thermometer code encoder, maybe, anyway, will be doubled for 1 extra bit. 2 extra bit means it needs to be 4 times larger. So the size of such kind of encoder will totally out of control. It will become too huge to occupy a lot of chip area. What we can do? Yeah, we are smart guys, okay? We are intelligent animals. Anyway, this is something can help. Matrix style current steering, matrix style, because in theory, the current sources is not arranged in a line, in a long line, in theory. Okay, so you turn it on from the right to the left, gradually, one by one. Okay, that is the logic thinking. However, to get more help or to reduce the size of such kind of encoders, this is a very good way. Now, the current sources, I mean, the logical thinking, or ideally, is not arranged to be a long line. No, they are again folded. All right? They are again folded to become a matrix. And then we need row decoder. Oh, sorry, that is decoder instead of encoder. Yeah. This is all minorly to thermometer code. Okay, minorly to thermometer code. Sorry, it is decoder instead of encoder. Anyway, we need two of them. One is for row, the other one is for column. Yeah. So what is the how can we operate such two decoders? Very simple. Yeah, you can see if for each row, if the output is 1, then it means what? All the current sources here for the row, I mean, needs to be turned on, all of them. All right? So, for example, if you have 2 here, okay? Yeah. So if this 1, 1, 0, 0, 0, blah, 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 all of them are zeros. So you can see here are 1, so all the rows are turned on. There is also 1, all of them will be turned on. So for the next, for the first 0, what does it mean? If it look back to its neighbor, it is 1. You are 1, I'm 0. Oh, so I'm the first 0 because 1 will be together, right? And zeros will also be together, okay? Nothing in between, only 1s and 0s. So according to the boundary between 1s and 0s, this is the first, okay? So for the first 0, it passes the control to the column decoder. And it means, I don't care. I wouldn't like to turn all of them on. So it's the responsibility of the column decoder, according to its input, to turn on the same number of the current sources. That's it. So here it is 3. So totally 1, 2, 3 is on. That's it. That is the operation principle. If you would like to ask me why we have such kind of a little bit strange structure or operation principle for such kind of matrix style current steering DAC. Okay, let's go back to the origin. So from the very beginning, we have 0 here, right? 0 there, right? So nothing to be turned on. Everything needs to be off. And then the next is 0 and 1. It means what? You need to turn on this, right? Then 2, 3, 4, 5, 6, 7, 8. Then you can see I have only 3 bits here. So what is for 8? Again, from 0 to 7. Keep this in mind. From 0, nothing is turned on. Then 1, 2, 3, 4, 5, 6, 7, right? 7 means 1, 1, 1, right? And then what is the next? It should be 1, 0, right? 0, 0, 1. And all those will be 0. Since this is 1, so here the output is 1. So everybody inside the first row will be fully turned on. Oh, bingo, that's it. Exactly, right? So after that, again, we have 0, 0, 1 here, and For LSB, it increased from 0, 0, 0 to 0, 0, 1. So again, here we have 1. Okay, so this one will be turned on. So 2, 3, 4, 6, 7. Sorry, 1, 2, 3, 4, 5, 6, 7. Right? 7. And then, here increase to be 0, 1, 0. So 2 of the outputs from the row decoder will be 1s. Right? So I'm also 1. So this one will also be turned on. Blah, blah, blah. So what does it mean? Here, according to the process I tell you, each time, if you get one extra output bits to be on, it means the row here needs to be fully on. According to the LSB changes from 1, 1, 1 to count up, right? To 0, 0, 0. Then the carry will be sent here to 10. One more row to be on. That's it. Okay. So that is some kind of maybe right now. I hope it is some kind of piece of cake for you to know what I claimed, what I explained from the very beginning. All the ones here will turn the corresponding rows fully on. And then for the first 0, I mean at the boundary of 1s and 0s, the first 0 will pass the control to the column decoder to decide how many current sources to be on. That's it. Okay. Yeah. That is the logic thinking. And then how to make it? Oh, yeah, allow me to show you this. From the hour, right? You can see if I am 1, then the control, this is from row. Okay, please look at this. This is the output, one of the outputs from row decoder, right? And that is one of the outputs from column decoder. So whether or not you would like to pass the control to the row decoder, it depends on myself. If I'm 1, sorry for that, I will turn all the current sources on here. You will get 1, right? Right? If I am 0, then I will pass the control. I will, because I'm 0. So the output will be 1 if column is 1. Okay? Or the output, if the column is still 0, then you get 0, blah, blah, blah. Okay. Anyway, anyhow, how to sense the boundary? That is the problem. Okay, let's go back here. How to sense the boundary between 1, 1 and 0, 0? So it means if I'm the first 0, then my neighbor, my upper neighbor, needs to be 1. Okay? So what is the logic you can apply to check whether or not I'm the first 0? Okay, very easy. You can say if I'm 0, so I get this, right? And then you need an AND gate. An AND gate, that is for your upper neighbor, and this is myself. See? So if I am 0, I will get 1 because here is the NOT gate, right? And my upper neighbor needs to be 1. Then, bingo. I am the first 0. Got it? All right. I explain everything for you, not only the logic thinking, but the implementation, how to make it. All right. So this is for you to refer. Yeah, I explained everything already. Oh, yeah, I can enlarge it for you. Okay. However, even though the manually weighted structure will provide the best performance, but the problem is if n, the number of base becomes too much, then, for example, if you have 10 bits, wow, sorry, you need to have so many unique current sources, right? If I am 14, oh, wow, more than, right? Or something, yeah, 15,000 or 16,000, I forget. Anyway, that is a huge number. The problem is, never mind, even for 10 bits, you have around 1,000 current sources. How can you ensure me? They will provide, all of them will provide exactly the same current for output. No, sorry for that. You need to, during implementation, you need to try your very best to make the output current about the same. I cannot say exactly the same. No way. Yeah, that is only in idea. In practice, nothing is perfect. After fabrication, you need to face again mismatch, right? So after fabrication, nothing will be exactly the same. Anyway, you need to try your very best to make all of them as close to each other as possible. But how? First of all, by calibration. Okay? Later I will explain how to calibrate the unit current sources, or by very good matching layout to cancel the systematic mismatch. All right? But we have two kinds of mismatches. One is systematic, which will be handled with very good layout or calibration. Okay? And the other one is random mismatch. How to handle it? A random mismatch depends on this, the standard deviation, right? Reversely proportional to the square root of the device area. It means for such kind of current sources, it has a lot of transistors. And for the current controlling transistor, the most important one, actually you need to care about it. Usually, we have code structure to enhance the output resistance. So who controls, this is N-type, all right? And that is the current output. Who controls the current? This one. It means the W by L instead of W over L. W by L needs to be large enough. Otherwise, the standard deviation of the output currents will be too much. Got it? Unless you have calibration. Okay, let's go back to calibration. If you have calibration, you don't need to pay attention to systematic or random mismatch, because you can calibrate the output back to the ideal value after fabrication. So you don't need to pay any attention to that. Otherwise, you need to be very careful. Layout pattern can help you to handle systematic mismatch, and the device area, yeah, will decide how good or how bad the random mismatch is. Okay, and for Monte Carlo simulation, it only handles the random mismatch. It has no idea about systematic mismatch. It means what? After you run the Monte Carlo simulation and you achieve good enough result, don't be too happy, because you still need to pay attention to good layout pattern. Otherwise, the output after fabrication will still be very bad. Okay, that's it. That is our poor life. However, again, it is also good to ensure your future, because IC design houses need a lot of engineers to finish all the dirty jobs. Okay. Till now, nothing can be automatic, all right? In our domain, I mean for analog design, especially for high-end analog chip design. Okay, so the problem is, if N becomes too much, you need to handle too many current sources, that is mission impossible because you need to match all of them. No, that is too much. Okay, so what we can do is you need to compromise between the unit current sources and minorly weighted current sources. And again, keep this in mind, which provide you the best performance? Unit current sources. So that is for MSB. Okay, and for the rest, LSB gets much less importance. So it can apply such kind of minorly weighted structure. So we call it hybrid or segmented current steering DAC. Segmented means we segment, we cut the overall structure from MSB to LSB. MSB bits with unit current sources and LSB bits with minorly weighted structure. There is a clear cut between MSB bits and LSB bits. So we call it segmentation. Okay, to cut it means to segment it. All right. And this is the usual case for a high-end DAC. You can see, all the current for MSB, all of them are unit, right? And for LSB, divided by 2, by 4, by 8, all the way, because they are not so important as MSB. Okay, so allow me to show you a very good example, 10-bit case. Yeah, for 10 bits, totally it has 7 bits for MSB, okay, and 3 bits for LSB. And here you can see 3 plus 4, okay. For 7 MSB bits, they are further divided into row bits and column bits. So here you have 3 plus 4 for MSB and plus finally the other 3 LSB bits. Got it? And in theory, all of them provide unit current output. Yeah, 1 unit. Okay, all of them provide 1 unit current output. And here divided by 2, by 4, by 8. Oh, that's it. All right. Anyway, anyhow, to make sure good enough accuracy, you need to focus on this very, very much. And for them, usually, for many of the papers I read, usually we let it be. Okay, you design it from the beginning, you have 1 unit for all of them, and finally this divided by 2. So how to make it? For example, only for example, okay? For the current control bit, you have this, okay? For the current control transistor, you make the final decision according to random mismatch. The aspect ratio for all of them is decided. And then how to make it divided by 2? Oh, very simple. Okay, by 4, by 8. That's it. Okay. However, that is only in theory. How about in practice? Okay, divided by 2 means what? 2 ways, either to double the length or to cut 50% of the W. Got it? It's up to you, not me. All right? Usually, we will enlarge the length until the maximum. For our process, we have design rule, right? We have DAC, right? According to design rule, you will know how long for each transistor it will be, the maximum length. Okay, so usually we enlarge it till the maximum length and then divide W. Okay, to ensure they can provide very good output resistance. Got it? Length, long length means good output resistance. Okay, that's it. Oh, finally, I need to remind you again. I need to warn you again. In last week, I tell you, if you do the layout in practice, just like this, oh, you have the first, the second, blah, blah, blah. Sorry for that. According to systematic mismatch, if I am larger than average, then my labels will also be more likely. They will be also larger than average. So it means what? Your DNL will have the same polarity, positive or negative, among labels. It's really harmful for INL, the most important specification for data converters. Got it? So you need to break the correlation or dependence among labels. How to make it? I told you already. You need to randomize the layout for them. So the real layout can never look like this unless you have calibration. Otherwise, don't do it. If you make your layout like this, I promise you, don't tell me, your ENAP, I mean according to INL, will be better than 12. No, will be better than 10. No, sorry for that. I guess even better than 8 bits is some kind of mission impossible. All right? According to systematic mismatch, it doesn't make any sense. You need to randomize the position for real layout. So I told you, maybe you can, 0 here, 1 there, 2 here, right? And then 3 and 4 and 5. Oh, okay. You need to randomize the positions. And then you need to route them back. A 0 is here, right? So you need to route all the 9 back to this position. Okay, and 1, and 2, and 3, and 4, and 5. Wow. It means what? The routing will become really messy, really complicated. Got it? Because you randomize the positions for all those labels. So after that, how to connect them to row decoder, column decoder, that is another story. The routing will become too complicated. So my next warning is, if the number of bits for MSB is too much, you had better go for help from EDA tools. Don't do it by your own hands. I mean, for layout, it will be too complicated. Our brain size is limited. We cannot handle such kind of very complicated routing. All right? Otherwise, yeah, I don't think you can make it, even for post simulation, because you will get a lot of error for your LVS, layout versus schematic. You need to pay years to make it. It doesn't make any sense. However, with the help of EDA tools, you can make it maybe within minutes. All right? That is the difference between humankind and computers. They are our slaves. Just tell them what we want. Then they can help you to implement everything. Okay, that's it. So finally, if you have calibration, then forget about it. You just do it 0, 1, 2, 3, all of them regularly, because you can enjoy such kind of regularity to simplify your layout very, very much. And after fabrication, everybody will go wrong, right? No worries, because we will calibrate to make sure all of them will provide almost the same output current. Okay? So, 2 ways for implementation. One is with very complicated layout, and the other is with complicated circuit design. Nothing is free. You need to pay for it, either for very complicated layout or very complicated circuit. All right, that's it. Anyway, again, this is something for differential output. You have positive output, negative output. So switch to the right or to the left. It depends on the control bit, the value of the control bit. And you need to make sure you will get real differential output, right? So everything to the right and to the left should be exactly the same. You have the so-called termination. We need terminator, right, to provide usually overall 50 ohms between all of them. So for differential output, yeah, you will have, okay? But in the past, humankind don't use 50 ohms for termination. In the past, we have 70. Oh, even for the very old TV sets, they have 300. So it depends on the specification of your cables. Yeah, output wire. For output wire, it has some kind of characteristic impedance, 特征阻抗. Okay, yeah, for such kind of impedance in the past and right now, usually 50. So for nowadays application, you need to make it 12 plus 12. Why? Simply because you can see here and there, they are of the same voltage, right? So in theory, they are connected. So for differential output, you look at from positive to negative, you need to see totally 50, right? Right? So everybody get 50% of the output termination. Okay, that's it. And then the other issue to remind you is for especially low supply voltage applications, you can see this is some kind of P-type. For N-type, you need to reverse your logic thinking. Okay, in theory, when the input, when the control bit changed, okay, for example, from 0 to 1 or 1 to 0. So it means what? Yeah, for example, from the beginning, I have 1 here, 0 there. And for the next clock, it will become 0. And the other one will become 1. Okay, so here it means what? It is off because that is PMOS. All right, I am off, you are on. So for next clock, I would like to be turned on. You would like to be turned off. Right? So you can see, I would like to be turned on from 1 to 0. Right? You would like to be turned off from 0 to 1. So in the middle, you can see, for me, I am off. And below the middle, I will be on. On the contrary, you are on. And above the middle, you will be off. Perfect. Right? However, nothing is perfect. Okay. So what will go wrong? Especially, again, for low supply voltage operation. Yeah, because the range is too small. So to turn it on, it is not in the middle. No, it needs to be low enough, right? So what is the problem? Here is a real threshold to turn on and off. So what is the problem? You can see, hey, for you, you are here, you are on, right? And above it, you are off. But you are here, I'm still there. So when you are off here, I'm still off. I have no time. I don't have enough time to turn on. Right? Right? So after when? After here, when I reach here, I will be on. So in between, both are off. That's it. That is the real problem. So when you and me both are off, what will happen? For current source, it hates very much to be turned off. According to its very high output resistance. So even you cut it off, the current source would try its very best to conduct the same output current. But how? Okay, it will charge the parasitic capacitance for this node. Okay? It will like to die, all right, to pass away. So it will try its very best to charge this one. So during the time you and me both are off, the node voltage will be charged sky high. And after I turn on, right, I can only push the node voltage back to normal. That is really bad for your output. Got it? For such kind of ripples on this node, because after I turned on, the node voltage will have some impact to your real output voltage. It is really bad. You will get a lot of ripples according to such kind of switching transition. Okay? So what we can do? Anyway, I told you already. Current sources hate very much to be turned off. So you need to make sure both those two cannot be off at the same time. So on the contrary, they can be both on. Got it? Okay. So the logic thinking is just like this. Only after I turned on. You need to make sure only when I turn on, after I turn on, you can be off. Got it? Got it? So for PMOS, this is to be turned on, right? From off to on, right? So from on to off needs to be postponed, needs to be delayed. Got it? 安尼讲你听有吼？我要拍开以前，你袂使关掉。啊，要安怎？你要慢一点。爱先互我拍开了，你才使关掉。Okay, so that's it. For the on to off, it needs to be delayed or postponed. But how to make it? Okay. See? It's a good idea. Yeah, you can see. Hey, for low to 1, you had better delay it, postpone it. But how? From here to there, if you would like to pull it up, it depends on PMOS, right? For this PMOS to pull the voltage up, right? But it needs to be delayed. What does it mean? The aspect ratio of W over L, right, of PMOS needs to be reduced. So it will react slowly. In the past, we would like to balance the conductivity because mu P is much less than mu N. So the aspect ratio for PMOS usually is 2.5 to 3 times larger than NMOS, right? That is to balance the conductivity. But right now, sorry, we need to postpone the response of PMOS. So it means what? The W over L of PMOS will be reduced from this value, less than 2 to 0.23 times larger. No. Smaller than this, okay? Maybe you can make PMOS, MOS are the same. I don't care, I don't mind. That is your own responsibility. After simulation, you will see how much less than this ideal value you need to make for PMOS. Okay, anyway, for the others, you simply have some kind of delay. Okay, that's it, I don't care. That is the same idea. Okay, for what? Again, to postpone or to delay the response of PMOS, to pull up 0 to 1 slower than 1 to 0. Okay, so again, I need to be turned on. After that, you can bit off. Keep this in mind. In this way, you can see, hey, look, turn off process is delayed, right? To reduce the glitch. Because everybody, the repos here will be turned on here or turned on there, will be connected to this output of that output. Got it? So it will have some kind of impact on the output. That's it. So you had better reduce it to make it as small as possible. So that is the consequence. You can see that is the original structure. Oh, the repo, the glitch is so high, right? But after delay or postpone the turn off process, you can see the repo for internal nodes. Okay, that is internal and that is external to the outside world, right? The voltage repo here will be substantially reduced from this one to that one. So again, how much delay you need or how much to reduce the aspect ratio for PMOS depends on your simulation. After you think, not me, okay? After you think the repo is small enough, has much less impact on the output than you make it. Yeah. And again, according to the accuracy you need to have, we have some kind of equations, calculations, blah, 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 all the way. That is in theory. So allow me to show you this. Okay? If you're interested, you had better Google online or search from IEEE Explorer, or maybe attend Professor Zhong's class. Yeah, he will derive or explain everything in theory for you, okay, in much detail for you. Anyway, that is the final result for you to follow. It means the more bits for your output, the more requirement for your design. That's it. Okay, yeah. According to such kind of final result, you can map it back to, again, the aspect ratio of your current controlling transistors. How much it needs to be. Okay, how large it needs to be. If its aspect ratio is not large enough, then sorry for that, you cannot fit this. Okay, that's it. All right. And finally, after the break, yeah, after I take back my coffee, right? before that, you will have a break. Yeah, I would like to tell you something very important for DAC design. It is called linearization. Why we need linearization? Oh, simply, as I told you from the beginning, never mind for any kind of, what kind of conversion, we hope the output look like this, right? That is your input, and this is the output. We hope the dependence look like this. It is a straight line. That is what we want. And how to measure the linearity? For data converters, we have INL, right? So if your output versus your input is perfect linear, then this one should be 0 in theory, right? However, if something goes wrong, then the output doesn't look like this. It looks like that. The INL will become too much. So you need to try to make such kind of nonlinear curve to become linear again. And that is what we call linearization. The technique to help you linearize your transfer curve or characteristic curve between input and output. Got it? To make the nonlinear output to become as linear as possible, and you can reduce INL. That's it. And what we have till now, you can see trimming. Really expensive. For example, for R string, right? What does it mean for trimming? After fabrication, everybody doesn't get the same resistance, right? So you need to measure one by one. How to measure? You need some kind of test pad or probing pad, okay, to measure the resistance and then think, oh, okay, too much or too small, blah, blah, blah. So it means what? All of them in theory needs to be variable. Okay, so after fabrication, you measure it, then you can fine-tune the resistance. And how about the current? The same, right? You have current, and the larger one, the smaller one, then you can fine-tune it. Okay, anyway, for trimming, for any kind of trimming or calibration, we don't make all of them available. For example, for this one, you have a always on resistor. Then the smaller one to be on or off. Okay, that's it. All right, and this is always on. The base resistance, the base resistor, and for the current source, the same. Even easier to understand. For each unit current source, all right. For each unit current source, it is composed by, this is always on, fixed, maybe 80% or 90% of the original value. And then some of the current sources to be turned on or off, usually they are minorly weighted, okay, to compensate for the variation after fabrication. Okay, but for example, here are 90%, right? Don't tell me you have 10% for tuning. No, much more than that. Okay? Because this is only the ideal value after fabrication. Sorry, maybe it will become 80 or even 70, right? So how much you need? More than 30. Okay, you can say, if after fabrication I become 70, so here I need to compensate for the other 70. That is in theory, but in practice, no. Why? Okay, if you look back the origin, I have 0.9. You have 0.3, right? And right now, 0.9 becomes 0.7 after fabrication. Me too. You are reduced from here to there. I will also be reduced from 0.3 to maybe 0.2 something. Okay? So if you add them up, sorry for that. No way. It is still not enough. Got it? Got it? The other issue is, hey, after fabrication, maybe it will be increased. So if you have 0.9, after fabrication, it becomes 1.1. Sorry for that. Even you turn all of them off, you still have more than what you need. You have no way to tune it back, right? Right? So, again, for such kind of trimming or calibration, this one you need to estimate if it goes wrong to be more, don't reach the ideal value. Got it? If you have, for example, 20% positive or negative, so you need to think, oh, if I get the maximum 20%, so it needs to be less than or at most equal to the ideal value. Got it? So in this way, you will know, IO becomes the ideal value divided by blah, blah, blah. So do it by yourself, by hand calculation. Piece of cake. Okay. I explained too much detail for this. Yeah, that is for trimming. Too expensive because you need to measure all of them one by one. Or analog calibration. Oh, yeah, it's really good. However, it takes time. Okay. Anyway, the circuit will become more complicated than without calibration. With calibration, compared to without calibration, the circuit will become much complicated. Okay, you need to pay for it, or you can pay for it by very good layout technique. Distributed, as I said, don't do anything like this. No, 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 no. Right? You need to spread the layout for all those neighbors as randomly as possible. So the circuit look very neat. Okay, very simple, just like this. Oh, that is a circuit. Very simple. But the layout is much complicated. 0 here, as I mentioned. So that is the two major ways. Either you need to pay for either very complicated circuit design or very complicated layout. Okay, that's it. So finally, we hope some kind of compromisation, self-trimming. Yeah, trimming is too expensive of the chip. However, if you can do it on the chip, then who cares? After power on, the chip will calibrate itself. You don't need any help from the outside world, then why not? Got it? That is a good way. I cannot say the best way, but a good compromisation among all of them. Too expensive, right? And this one too complicated for circuit design, and this too complicated for layout. So a good compromisation is to trim it by yourself, by the chip itself, after power on, okay? To make everything good enough. In this way, you need the help from digital circuit. Again, it is some kind of distally assisted analog circuit. That is what I told you. So after this break, I will tell you how to calibrate the circuit by itself. Self-trimming, self-calibration. Okay? Yeah, let's have a break. Then we'll come back for this very interesting and excited idea.